This is a video for AQA Further Pure Mathematics, Sequences and Series section 4.1, which looks at finding a polynomial approximation. Well, we've seen in previous videos how polynomial approximations, i.e. functions of the form a plus bx plus cx squared, etc., can be used to approximate functions. What we want to do in this section is to see how we can evaluate the coefficients a, b, c to make the approximations get better and better as we increase the order of the polynomial. So, as an example of how we proceed, I want to consider the equation for f of x, which is e to the x. So that's the function that we want to approximate. And we could start off by looking at a linear approximation. In other words, p of x equal to a plus bx. Now we can make sure that we get a good fit at x equal to 0 by making sure that the function has the correct value. So we can say that we want f of 0 to be equal to p of 0, and also has the correct gradient. So we want f dashed of 0 to be equal to p dashed of 0. If p of x is equal to a plus bx, then p dashed x, the first derivative, is obviously equal to b. And f of x equal to e to the x, the derivative f dashed x is equal to e to the x. So p of 0 is equal to a, and f of 0 is equal to e to the 0, which is equal to 1. And therefore we have that these mean that a must be equal to 1. P dashed of 0 will be equal to b, and f dashed of 0 will be equal to e to the 0 again, which is 1. And therefore b equals 1. So we can say that our linear approximation, p of x, must be equal to 1 plus 1x. So making the value of the function at 0, i.e. 1, and the gradient of the function at 0, which is also 1, agree with the polynomial approximation, we get our polynomial approximation 1 plus x. And we can see therefore that close to x equal to 0 anyway, this is a reasonable approximation. If you look in this area here, you can see it's good, but obviously the further we get away from that point, then the more error that creeps in. So what we can then do is look at higher order polynomials. So instead of just looking at the value of the function and the first derivative, we also look at the second derivative. Well, the value of the function and the first derivative are the same as before, but this time we want to look at the second derivative as well. Well, p double dashed of x will be equal to 2c, and for e to the x, again, the second derivative at 0 will be equal to 1. So we have that 2c is equal to 1, which means that c is equal to 1/2. So we get our second order approximation, 1 plus x plus 1/2 x squared. And we can see therefore that we've got this curve here, and now the area in which it is a good approximation is getting rather larger. So we can continue in the same way then, looking at higher derivatives, so the third derivative and fourth derivative, and each time making sure that the polynomial agrees with the value of the function at 0. Well, this GeoGebra file shows the result of doing that. So at the moment we've got it set for n equal to 2. In other words, the second order polynomial that we have already found, 1 plus x squared over 2. And this just shows that as we increase from 2 to 3, then the polynomial obviously change into a cubic, then a quartic, and so on, and each time getting closer to the function itself, and the range of values for which it is a very good approximation increasing each time. And we can keep going so that we get as close as we desire in any particular range. So we can apply this approach to a wide range of functions. The important thing is then that the function and its derivatives can be evaluated at x equal to 0. Now here's an example where we've got the approximation order 7 to the function f of x equals sine x. And you can see that this polynomial here, which is of x to the power 7, is a very close approximation to sine x close to x equal to 0. In fact, it's very close in the range from negative pi up to pi. Well, in the next video we'll be looking at Maclaurin's series, which is really just a generalized approach of what we've just been looking at.